Welcome back to the 10th installment of my series on Earth's extinction events. Today, we're diving into the Neogene Period, a time that didn't see mass extinctions on the scale of the Permian or Cretaceous. Instead, the Neogene was marked by regional extinctions, faunal turnover, and gradual declines in some lineages. If you're new to this series, don't worry, this video stands on its own. But if you're curious about earlier mass extinctions, check out the full playlist. If you'd like to dig deeper, I've linked a document in the description with all the sources and image credits used in this episode. The Neogene period was the second and middle period of the Cenozoic era, lasting around 20 million years, from about 23 to 2.58 million years ago. Notably, this end date was revised in 2009 when geologists redefined the boundary between the Neogene and the following Quaternary period. Previously set at 1.81 million years ago, the boundary was moved back to 2.58 million years ago to better reflect a key climatic shift, the onset of widespread glaciation in the Northern Hemisphere. This change gave the period a firmer stratigraphic and climatic foundation. The Neogene comprises two epochs, the Miocene and the Pliocene, and was marked by significant transformations in global climate, ecosystems, and animal evolution, especially among mammals and birds. The climate was generally warmer than today's, but the Earth was already well into a long-term cooling trend that had begun in the Eocene. This cooling became more pronounced through the Miocene and especially into the Pliocene, as polar regions cooled further and permanent Antarctic ice sheets expanded. By the end of the Neogene, Earth entered a new climatic phase, with the development of major glaciations in the Northern Hemisphere for the first time in the Cenozoic. This shift heralded the colder, more variable climate of the Quaternary. Changes in ocean and atmospheric circulation also played a role. The formation of the Isthmus of Panama, which connected North and South America, closed the Central American Seaway and reshaped global currents. This likely redirected warm ocean water and moisture toward higher north latitudes, increasing snowfall and promoting ice sheet growth. Plant life during the Neogene changed dramatically as the global climate became cooler and drier. In the early Miocene, forests were still widespread, including tropical and subtropical forests in many regions. But as temperatures fell and rainfall patterns shifted, grasslands and open woodlands began to replace dense forests, especially in temperate regions like North America, Central Asia, and parts of Africa. One especially important development was the spread of C4 grasses, a new type of grass that could survive in hot, dry environments and made better use of sunlight and carbon dioxide. These grasses became dominant in many open landscapes, such as savannas, steppes, and prairies. Their success transformed ecosystems, supporting large numbers of grazing animals like horses, elephants, antelopes, and bison, and shaping the evolution of predators that depended on them. In temperate regions, deciduous forests became more common, and in colder or dry areas, coniferous forests, scrublands, and even deserts expanded. Overall, Neogene plant life became more adapted to seasonal climates and variable rainfall, setting the stage for the types of ecosystems we recognize today. The changing climate and expanding grasslands of the Neogene had a major impact on animal life. Many mammal groups became adapted to life in open, drier environments. Grazers and browsers became more diverse and abundant, and many evolved new teeth and limb structures suited for running and feeding on tough, fibrous grasses. At the same time, predators evolved alongside them. Early members of modern carnivore families, including cats, dogs, and hyenas, became more specialized for chasing prey across open ground. In the oceans, life also flourished, with the appearance of many modern groups such as whales, dolphins, seals, and sea lions, while massive marine predators, like the giant shark megalodon, roamed the seas. Birds evolved alongside mammals, filling ecological roles in open habitats as scavengers, hunters, and seed dispersers. Large, flightless birds remained dominant in some regions, especially where mammalian predators were absent. Reptiles, such as snakes and lizards, continued to thrive in warmer climates, while amphibians persisted in wetter areas, though some declined as environments dried. Insects also responded to the changing world. Grasslands supported a large number of pollinators like bees and butterflies, while ants and beetles adapted to new niches. These insects played essential roles in pollination, decomposition, and soil formation, and were key in maintaining the evolving ecosystems of the Neogene. By the end of the period, hominins, early human ancestors, were appearing in Africa. These upright walking primates began to use tools and show early signs of modifying their environment, a shift that would eventually lead to the emergence of Homo sapiens in the Quaternary. While the Neogene period is often characterized by gradual climate cooling and evolving ecosystems, it also experienced several distinct episodes of environmental upheaval that caused notable extinctions and faunal turnovers. Understanding these key events helps us see how life responded to rapid changes amidst the long-term trends. One of the more mysterious and underappreciated extinction events of the Miocene occurred not on land but in the oceans. Around 19 million years ago, sharks suffered one of the most abrupt and severe diversity crashes in their entire history. Fossil evidence from deep-sea sediments shows a sudden 90% drop in global shark populations, along with a major loss in body forms and ecological diversity, especially among species that lived in the open ocean. Many large, fast-swimming predators disappeared, and the groups that survived were far less diverse. This little-known extinction reshaped shark evolution, leaving today's open ocean sharks, like makos, blue sharks, and great whites, to rise later and fill the vacant roles. Even now, the low diversity of pelagic sharks may reflect the long shadow of this ancient collapse. What caused it is still a mystery. Unlike other extinction events, there's no obvious culprit. No asteroid, no sharp climate shift, no massive volcanic outburst. It stands out as a sudden loss with few clear explanations, highlighting how much we still have to learn about ancient marine ecosystems. Following the earlier but still puzzling shark collapse, the next major upheaval came around 14.5 million years ago with what's known as the Middle Miocene disruption, a turning point that triggered widespread global cooling and reshaped both marine and terrestrial ecosystems. This cooling event interrupted the long phase of relative warmth and stability that had persisted since the late Paleogene period. Global average surface temperatures are estimated to have dropped by about 4 to 5 degrees Celsius during this time, marking a significant turning point in the Earth's climate. The disruption is believed to have been driven primarily by the expansion of Antarctic ice sheets and changes in ocean circulation patterns. But these weren't the only forces at work. Tectonic activity, particularly the continued uplift of the Himalayas and Tibetan Plateau, has long been proposed as a contributing factor. As these mountain ranges rose, they exposed fresh rock surfaces to the atmosphere, a process thought to enhance chemical weathering, which in turn draws carbon dioxide out of the air. This mechanism has often been cited as a driver of long-term cooling during the Neogene. However, the picture may not be so straightforward. Recent studies of the Indus River system suggest that weathering rates in the region may have stayed the same or even have declined in some areas. This raises questions about how effective the uplift was at drawing down CO2, particularly if cooler and drier conditions limited the amount of rainfall needed to drive chemical weathering. As a result, the role of Himalayan uplift in climate change during the Miocene remains an open and actively debated question. Whatever the cause, atmospheric carbon dioxide levels were indeed falling, and this trend is widely seen as one of the key factors behind global cooling. Changes in ocean gateways, such as the restriction of the Indonesian seaway, likely altered heat and moisture transport around the globe, reinforcing the shift towards cooler and drier conditions. Some researchers have also speculated about longer-term climate influences, such as orbital cycles or even galactic scale patterns, like the proposed Redcliffe wave, which imagines periodic climatic shifts tied to the solar system's movement through the Milky Way. These ideas remain intriguing but speculative. As the planet cooled and ecosystems shifted, life began to respond in dramatic ways. On land, the retreat of dense forests opened the door for more arid habitats, including savannas and grasslands. This change spurred a major turnover in faunal communities. Mammal groups that had thrived in forest environments, such as some primates and small browsing species, declined in many regions. In their place, more adaptable grazers and mixed feeders gained ground. Hoofed animals like horses, antelopes, and camels diversified, evolving limbs suited for running and teeth adapted to tougher, grass-based diets. Predators followed suit. Carnivorous mammals adapted to hunting in more open landscapes, reshaping food webs alongside their prey. Birds of prey and other open country birds also took advantage of these expanding habitats. In the oceans, falling temperatures and changing currents disrupted marine ecosystems. Coral reefs contracted in many tropical areas, and warm water species like certain mollusks and foraminifera declined or vanished. These changes rippled through marine food chains, affecting fish, marine mammals, and seabirds alike. Although the Middle Miocene disruption didn't cause a mass extinction in the classic sense, it was a time of profound ecological transition. Many species disappeared, while others adapted, radiated, or shifted their ranges in response to the new environmental realities. It marked a biological turning point that set the stage for the evolving ecosystems of the late Miocene and beyond. Following the abrupt climatic changes of the Middle Miocene disruption, the late Miocene was a period of more gradual but persistent ecological pressure. Temperatures continued to fall, and aridification spread across much of the globe. Forests that had once dominated large swathes of Europe, Africa, and North America continued to shrink, giving way to expanding grasslands and open woodlands. This shift didn't trigger a sudden extinction event, but rather a drawn-out process of faunal turnover lasting from around 11 to 5 million years ago. Many mammal groups, particularly large browsing herbivores, adapted to lush forest environments, declined across their ranges, or disappeared entirely. Marine life, too, showed signs of thinning biodiversity, especially among warm water species like mollusks and foraminifera, as ocean temperatures cooled and nutrient patterns shifted. This slow fade in biodiversity is sometimes referred to as the late Miocene extinctions. Not a formal mass extinction, but an extended phase of biotic stress and faunal turnover. Its effects were widespread but uneven, acting as a prelude to the sharper ecological disruptions to come. Among the most dramatic of these was the Messinian salinity crisis, which played out not on a global scale, but within the confines of a single area. Toward the end of the Miocene, one of the most extraordinary environmental events of the entire Cenozoic unfolded. Not across the globe, but in a single iconic body of water, the Mediterranean Sea. Around 5.96 million years ago, tectonic shifts closed the connection between the Atlantic Ocean and the Mediterranean basin. This narrow marine link, like the precursor of today's Strait of Gibraltar, had been keeping the Mediterranean filled with seawater. Once it was blocked, evaporation started to remove water faster than it could be replaced by rivers and rain. The result was dramatic. Over the course of hundreds of thousands of years, the Mediterranean partially, and perhaps nearly entirely, dried up. This period is known as the Messinian salinity crisis. Salt layers hundreds of meters thick built up on the sea floor as water levels dropped and the remaining water became extremely salty. Vast salt flats, isolated brine lakes, and a deep, hot basin replaced what had once been a thriving marine environment. Sea life struggled to survive. Many species of fish, mollusks, and plankton adapted to open marine conditions died off within the basin, leading to a wave of local extinctions. Coral reefs disappeared, entire ecosystems collapsed. The surrounding land was affected too. The basin floor may have sunk by over a kilometre, creating steep cliffs and altered wind and weather patterns in the region. Some researchers have even speculated that these extreme environmental gradients may have shaped migration routes, influencing the dispersal of animals, potentially including early hominins, between Africa and Europe. Then, just as dramatically, the crisis ended. About 5.33 million years ago, the sea passage reopened. In what's often referred to as the Zanclean flood, seawater from the Atlantic surged back into the basin at an astonishing rate, possibly within a few years or even days. In geological terms, this occurred almost instantly. The Messinian salinity crisis is not considered a mass extinction in the traditional sense. Its effects were highly regional, but for the marine ecosystems of the Mediterranean, and for the landscapes and climates surrounding it, it was a profound, even surreal transformation. It stands as a reminder of how local geological events can trigger ecological changes on a scale that is almost unbelievable. Following the Neogene's long chapter of gradual cooling and regional upheavals such as the Messinian salinity crisis, Earth entered a new era defined by global climatic shifts. Around 2.58 million years ago, the boundary between the Pliocene and the Pleistocene epochs marks the beginning of the Quaternary period, a time when ice sheets grew and shrank repeatedly in the northern hemisphere, shaping much of the planet's modern environment. This transition brought major changes in climate and ecosystems worldwide. Large-scale glaciations, known as ice ages, began in earnest, with glaciers expanding across North America, Northern Europe, and Asia. These icy advances weren't just cold spells, they transformed habitats, altered sea levels, and caused repeated cycles of environmental stress. Marine ecosystems felt the effect too, especially in coastal and shallow waters, where fluctuating sea levels and colder temperatures led to shifts in species composition. Many marine animals that thrived during the warmer Pliocene struggled to survive in these new conditions. On land, animals faced changing landscapes as forests gave way to open grasslands and tundra in northern regions. Some species disappeared, but many adapted to the cooler, more seasonal climate. This was also a critical period for human ancestors, whose increasing adaptability and migration during these shifting environments laid the groundwork for later human evolution. One of the less obvious but important transitions during this time was the rise of modern carnivores. Earlier predator lineages, like the extinct bone-crushing dogs and nimravids, began to disappear, replaced by more familiar groups. Canids, the ancestors of wolves, foxes, and domestic dogs, expanded into new territories, while felids, the true cats, diversified and rose to ecological prominence across multiple continents. Other groups, like hyenas and bears, also gained ground, particularly in Eurasia. These shifting predator communities helped reshape food webs and influenced how herbivore populations responded to the evolving climates and landscapes of the Pliocene and Pleistocene. As mentioned earlier, this transition aligns with the updated boundary marking the end of the Neogene and the start of the Quaternary, highlighting the significance of these widespread glaciations. By redefining the boundary to this point, scientists created a clearer and more meaningful division based on major global climatic shifts rather than a less distinct event. In many ways, the Pliocene-Pleistocene represents Earth's move from a relatively stable and gradually cooling world to one dominated by rhythmic ice ages, environmental unpredictability, and new opportunities and challenges for life. The dramatic climate shifts in the Pliocene-Pleistocene boundary didn't just reshape ice sheets and landscapes, they also triggered significant changes in animal communities around the world. In the northern hemisphere, the repeated advance and retreat of glaciers forced many species to adapt, migrate, or face extinction. Large mammals, such as mastodons, saber-toothed cats, and some giant ground sloths disappeared, while others evolved traits to cope with colder, more seasonal environments. Species like woolly mammoths and bison developed thicker coats and specialized diets to survive the Ice Age conditions. But the effects weren't confined to the north. Even in regions far from the glaciers, such as South America and Australia, ecosystems experienced ripple effects. South America, for example, saw changes in habitats as cooler, drier climates replaced some forests with grasslands and open woodlands. This shift favored grazing animals like camelids and influenced the evolution of native predators. Australia, largely isolated from northern ice ages, nonetheless faced its own environmental challenges. Shifts towards cooler and more arid conditions likely contributed to the decline of some megafauna, such as giant marsupials and large flightless birds, though the exact timing and causes remain subjects of ongoing research. Across continents, the Pliocene-Pleistocene climate oscillations increased environmental unpredictability. Animals that survived did so through flexibility, changing diets, migrating to favorable areas, or developing new behaviors. Some groups thrived by exploiting newly expanded grasslands, while others became more specialized to cope with shrinking habitats. Overall, the transition marked a time of considerable faunal turnover. Many species vanished, but many others adapted, setting the stage for the ecosystems familiar to us today. These global patterns of extinction, adaptation, and migration highlight how climate-driven environmental changes shaped life across continents during this dynamic period. Not all species responded to climate change by going extinct or migrating long distances. In many regions, pockets of stable habitat, known as refugia, offered temporary shelter from the worst of the environmental swings. These refugia allowed some plants and animals to persist through glacial extremes, then recolonizing surrounding areas when conditions improved. For example, parts of Southeast Asia retained humid forest conditions even as much of the region dried out during glacial periods, helping explain the incredible biodiversity of its rainforests today. Similar patterns played out in other regions too, like southern Europe or Eastern Asia, where sheltered valleys and coastal zones protected forest flora and fauna through the most intense glacial cycles. The global shifts in climate were not the only forces influencing faunal turnover at this time. While glaciations and cooling reshaped habitats and ecosystems, another dramatic event was unfolding, this time driven by geology. The Great American Biotic Interchange, or GABI, that is GABI, was a major biological event that occurred when North and South America became physically connected for the first time in over 100 million years. This began in earnest around 2.7 million years ago, when the Isthmus of Panama finally rose above sea level and formed a land bridge. Until then, South America had been effectively isolated, developing a distinctive and often bizarre range of animals, including giant ground sloths, terror birds, glyptodons, and an array of marsupials. In contrast, North America was home to carnivores like bears and saber-toothed cats, and grazers such as horses, deer, and camels. When the land bridge formed, it allowed animals to move between the continents. North American species like felids, canids, and hoofed mammals headed south, while South American animals such as armadillos, porcupines, and opossums moved northward. But this exchange wasn't entirely balanced. Far more North American species became established in South America than the other way around. Possible reasons include competitive advantages, differences in habitat, or ecological momentum. One of the most surprising participants in this exchange was the camel. While camels are now associated with deserts in Africa and Asia, they actually evolved in North America. Some of their ancestors migrated south during Gabi and eventually gave rise to modern species like Vicuña and Guanaco. I covered that fascinating journey in more detail in a separate video on camels and llamas if you'd like to explore that further. Many of the animals we associate with one continent today are, in fact, products of this ancient interchange. The Virginia opossum, for instance, is a South American native that now ranges across much of North America. On the flip side, modern South American ecosystems still feature familiar North American immigrants, like deer, raccoons, and even bears, whose distant relatives made their way south. This is why sloths live in South America, but so do species like the spectacled bear, descended from northern ancestors. It's worth noting that the Great American Biotic Interchange didn't happen all at once. It played out over hundreds of thousands of years, with waves of migration and extinction as ecosystems adjusted to the sudden influx of new species. But the long-term effects were profound, permanently reshaping the biodiversity of the Americas and contributing to the ecological structure we see today. Gabi was just one part of a much larger story playing out across the globe. In many ways, it exemplifies the turbulence of the time, when shifting climates, changing landscapes, and the breaking and forging of continental connections drove ecosystems into constant flux. Just as glaciations transformed the North and drying climates reshaped the tropics, the collision of North and South America upended long-standing ecological boundaries. The result was a world in transition, defined not by stability, but by movement, extinction, and adaptation. A fitting close to the Neogene, and a prelude to the even more dramatic changes that would define the Ice Age world of the Quaternary. I hope you enjoyed this video. The Neogene is a fascinating chapter in Earth's history, a time when the cooling climate reshaped continents, transformed ecosystems, and set the stage for the Ice Ages to come. Next week, we'll return to one of my more traditional videos, investigating some strange predatory water bugs. But for this extinction series, we have just one more stop in this journey, the Quaternary Period, from the first Cenozoic Ice Ages all the way up to the present day. Thanks for watching, and as always, let me know your thoughts in the comments below.